Hello, everyone. We're here with John Weisend, editor of Cryogenic Technologies at the European Spallation Source. Mr. Weisend is a senior accelerator engineer at the ESS and adjunct professor at Lund University in Sweden. He is chief technical editor of Advances in Cryogenic Engineering and the chair of both the International Cryogenic Engineering Conference Committee and the Cryogenic Society of America. He is also author and an editor of various other titles, including Keys for Helium and Cryogenic Safety. Thank you for your time today. Can you please tell us about your work at ESS?
So yes, for the bulk of my time at ESS, I've been there since 2012. I served as both the deputy project manager for the accelerator project, assisting the project manager for the accelerator project with project management things. And then on the technical side, I was the head of what was known as then as the Specialized Technical Services Group, which was responsible for all cryogenics and vacuum systems in the laboratory. And we are just beginning to end being a construction project. So my responsibility and that group's responsibility was to procure, design, and build and commission the cryogenic and vacuum systems throughout ESS.
Thank you very much. Could you please tell us what the target audience is for the book?
So the target audience of the book are engineers and scientists that work in cryogenics, particularly large-scale cryogenics, and also on accelerator projects. But the somewhat broader audience are people not only just working in cryogenics, but people working in large-scale international collaborations for science, particularly those that are beginning to use this model of in-kind contribution, which was a major part of how ESS was put together. And so the book addresses, in addition to describing the technical systems, what we learned along the way in organizing and managing these large international collaborations with in-kind partners.
Thank you. Could you please talk about the book structure and the division of chapters?
Sure. The first thing to realize is that the bulk of the content of the book was written by the chapter authors. And these authors were all experts in the systems. They were, in fact, responsible for the procurement and installation commissioning of the systems about which they talked about. The book is divided into an introductory chapter and then a series of chapters, one of each covering each of the major cryogenic systems at ESS, and including the two test stands that we use for testing cryo modules. And our authors came from ESS itself, as well as in-kind partners at Uppsala University and in France.
Thank you. In a few sentences, can you tell us what the role of cryogenic systems in the ESS project is?
Yes, so cryogenics is an enabling technology for ESS. ESS is a neutron source where we create the neutrons by accelerating high-energy protons in a linear accelerator, use those protons to strike a tungsten target. That interaction between the protons and the tungsten generates neutrons, which then go out to various instruments, and we use the neutrons to make fundamental studies in material science, biology, chemistry, and so on. ESS plays a role in all three of those areas. Cryogenics, plays a role in all three of those areas. We provide the cooling for the superconducting RF cavities that provide the bulk of the acceleration in the accelerator. We provide the cooling for the liquid hydrogen moderator that surrounds the target and slows the neutrons down to an energy that is useful for the scientists. And we provide a role in the instruments itself, providing liquid helium to provide low temperature environments and cool superconducting magnets. So it's a major part of the ESS project.
Can you please tell us more about the cryogenic safety at ESS?
So yes, cryogenic safety was built in from the beginning, which is a very important point. You really have to do that from the start of the design and not try to back design it in later. So from the very beginning, we thought about cryogenic safety. ESS has to meet and has met all the cryogenic safety rules by the European Union, and these include the pressure vessel rules and the various rules involving inert gases. And it also has to meet the local Swedish rules where they also, in cases where they also apply. So we've done that from the beginning. We had extensive reviews of cryogenic safety. Pretty much every time we had a design review or an installation review, safety was on the list of topics covered. And we followed more or less standard cryogenic safety practices that have been developed either by regulation in the EU and Sweden or through experience at other large-scale helium cryogenic facilities. One of the features of ESS is that we were a greenfield lab, and we really only started as a laboratory in 2009, and we really only started construction on the site in 2014. So when we were developing the cryogenic safety rules, we were working closely with our environmental safety and health division to decide what the actual rules we would follow at ESS. And since the cryogenic systems were some of the earlier systems ordered, we were in effect working with them to create the site-wide rules for cryogenic safety. And people in the cryogenics group and myself still to this day are on safety reviews and consult frequently with the ES&H department on these sorts of issues.
So you said about the safety, but I also want to ask you about the environmental impact, because in the book it says that a major aspect of the Swedish-Danish bid to host ESS was the commitment to build a sustainable laboratory and minimize the environmental impact. So could you please give us some examples of that?
Yes, this is actually a fairly unique part of this project because again, that was part of their initial bid was to build as green a facility as possible. The best example of this comes in the area of waste heat recovery. Most cryogenic and accelerated facilities will use cooling towers or cooling ponds to absorb the waste heat that's generated or extracted from the systems as you cool them down. At ESS, what we do is we use that heat to heat the local domestic hot water system in the region of Lund. And so that heat is actually recovered. About 50% of all the heat we generated on site is actually recovered and reused either for site buildings or for the broader domestic hot water system. And this is a very unique facility. I think we're the only facility that does this to this extent. We also have a commitment to use where possible green energy to power the ESS. Now we're tied to the Swedish national grid, and so we don't know where the electrons come from. Though the bulk of the Swedish electrical system is in fact non-fossil fuel based. It's mostly water, nuclear, and some wind. But what we do is we do purchase credits that help fund wind farms and other renewable energy sources as part of our electricity procurements. We also, of course, put a lot of effort into recycling. All our construction waste was recycled, and our operating waste is recycled to the extent possible. And wherever possible, we used sustainable materials. That was always a key question of when we were looking at building and designing things.
So what advice would you give to other researchers or engineers working on similar large-scale cryogenic projects?
So we had a number of lessons learned, and one of the features of the book is that each of the chapters ends with a series of lessons learned associated with that particular cryogenic subsystem. Some of these are technical lessons learned, but the bulk of them really are organizational and management sorts of things. And of those, the two really key ones are in an environment where you are working with in-kind partners, where you have people who are contributing, as they did to us, not cash, but actual components and expertise. You have to work very closely and develop very strong relationships with them at all levels of the organization. You simply can't, write a contract and expect everything to work properly. You really have to treat these partners as collaborators, which is what we did, as opposed to subcontractors. And we had developed very strong relationships all the way from the director down to the working engineers. And that made it very easy so that when problems arose, we were able to work together to solve those problems. So having really strong relationships with in-kind partners from the beginning and treating them as equals in the project, I think is one of the reasons that this work succeeded as well as it did. The other key one is that you really want to hire as soon as possible the best people possible for your project. In the case of ESS, we had the advantage that we could hire from anywhere around the world, even though we're a European project funded by 13 European nations. We could hire from around the planet. We have people from more than 55 countries currently working at ESS, and some of those countries have substantial contributions as ESS employees. And that allowed us really to pick the best people we could find for the various roles. And we got them in as early as possible. In the case of the cryogenic system, we hired in technicians and operators very early in the process so they could be present when the subcontractors, when the industrial vendors, Air Liquide and Linde, came in and installed equipment and commissioned it. Our cryogenic operators and techs worked side by side, so they learned all the details, learned all the quirks of the various equipment so they could operate it efficiently and know how to use it. And I think that's an important advantage as well. Other things are, make sure you give yourself enough time. This is always a fight in projects because projects tend to have short time spans, but you want to try to fight early on in the project, have sufficient time to fully test everything before it has to operate. You want to, if it's a new site like ours was, you want to involve yourself closely with the civil construction people to make sure the buildings and utilities meet your needs, and then occasionally have to push your needs to make sure this gets done. And then there are a number of other smaller ones that go along with that. But those are the key takeaways, I think.
Thank you so much. And finally, how do you see the future of cryogenic technologies involving in big size facilities?
So I think the future is very strong. There's a number of large scale accelerator facilities and fusion energy facilities that are using cryogenics and will use cryogenics. These include 3 large accelerators currently under construction in China, one's under construction in the United States. Follow-ons to LHC, any of those are likely to use cryogenics at large scale. And then there are also fusion ones, such as ITER and any follow-on to ITER, as well as the smaller privately funded fusion projects like Spark, which also use superconducting magnets. So I think there's a large array for the next 20 years of these sorts of projects that will use cryogenics. And then going a little further, quantum computing, which is becoming more and more important and showing a lot more interest, also needs very low temperatures, generally sub-Kelvin or sub 4.2 K temperatures to operate. And then, of course, sort of in parallel that is anything having to do with any hydrogen economy. If we start to use hydrogen as a fuel, using liquid hydrogen, which is a cryogenic fluid, to transport and store that fuel may be a major part of that process. So it's a growing industry in these fields.